So my name is Faris Antaki. I'm one of the co-chief residents here at the department. And today I'll be talking about automated machine learning to diagnose retinal disease from ultra-wide field photos. I'd like to thank my co-authors from the University of Iowa, the CHUM and Maisonneuve-Rosemont hospitals. Thank you, Dr. Duval. Here are my conflicts of interest, none of which are related to the content of this presentation. The field of medical and surgical retina is at the intersection of medicine and technology. And today, retina specialists routinely rely on high quality, high resolution imaging of the retina to diagnose, treat, and monitor patients. As such, large imaging data sets can be gathered and analyzed using artificial intelligence methods to identify disease types and stages, and even provide information regarding response to treatment and prognosis. Until recently, the development of AI models had been reserved to experts with coding skills, a skill that is out of reach of most clinicians and ophthalmologists. This is up until the rise of automated machine learning. Automated machine learning is a type of platform that's been released by major tech companies like Google and Microsoft, and it constitutes a major step for the democratization of AI. By automating complex tasks in the machine learning design pipeline, it has allowed users like myself to develop high-quality AI models without writing a single line of code. In this study, two ophthalmologists designed AI models using a no-coding interface in the Google Cloud AutoML vision platform. We aimed to train a model that could distinguish and diagnose retinal disease from ultra-wide field photos. We really sought to answer a simple question: can a deep learning model designed by ophthalmologists without coding accurately diagnose retinal disease from an ultra-wide field photo? To answer this question, we chose three distinctive retinal pathologies: retinal vein occlusion for the presence of hemorrhage, retinitis pigmentosa for the presence of RPE changes, and retinal detachment for the presence of retinal elevation. And although clinically obvious, the distinction between hemorrhage, RPE changes, and retinal elevation has not been previously validated using AutoML. For that, we used a publicly available dataset provided by the Tsukazaki Optos Public Project that included more than 13,000 ultra-wide field images acquired using the Optos machine. Through a robust dataset preparation methodology, we narrowed it down to a final dataset of 2,137 images, including normals, RVO, RP, and RD cases. We split the dataset 80% for training, 10% to fine-tune the model, and 10% to test it. Our ophthalmologists built the deep learning models in a no-coding platform that they accessed using their internet browser, whether it is on their phone or their computer. They used a simple point-and-click interface to upload the images and adjust their labels. Hours later, the platform provided us with interpretable results on how well the model could diagnose the retinal disease. Our first model needed to distinguish retinal vein occlusion from normal fundus photos, and it had very high prediction capacities. The area under the precision recall curve, which is a metric that ranges from 0.5 to 1, was very high. We had high sensitivity, specificity, and positive predictive value. And our model did well with most evident cases of CRVO, but also in least evident cases with only mild venous engorgement and tortuosity and mild dot and blot hemorrhage. The case of retinitis pigmentosa was similar: high AUPRC, high sensitivity, specificity, and positive predictive value. And our model did well in most evident cases with diffuse bone spicule-like pigmentation, and also mild cases or least evident cases with hypopigmented RPE changes. The case of retinal detachment was similar. Our model did very well. It had slightly lower performance, but it had high sensitivity, specificity, and positive predictive value, approaching 90% which meant that 9 out of 10 times when it made a retinal detachment diagnosis, it was right. It did that in most evident detachments, but also in least evident cases with only an inferior infratemporal shallow detachment without a visible break. The next step was to simulate real life. We wanted to create a single model that could simultaneously diagnose RVO, RP, RD from normal fundus photos. And our model did well with a positive predictive value of approximately 83%. 8 out of 10 times it was right when it diagnosed RVO, RP, RD, or normal fundus photos. The next step when you develop an AI model is to externally validate it on types of images it had never seen. So we went online and compiled a data set from Google Images, the ASRS library, and Retina rocks. We generated a heterogeneous data set that included ultra-widefield photos, but also ultra-widefield photos that were zoomed, cropped to the macula. And we included a different range of color blends, which are percentages of red to green on the Optos machine. And our model did very well. It had high metrics, making the right diagnosis more than 9 times out of 10. This is great, but the main question and the main limitation towards clinical acceptance of AI models is the black box nature of artificial intelligence. What is this deep learning model actually looking at? And this is even more true in the case of AutoML, because we have very little insight into the model architecture because we're not writing any line of code. And for the first time with AutoML, we're able to show you heat maps, saliency maps, highlighting the areas of interest based on which the model made its prediction. This is a first step towards explainable AI that makes sense. On the left, you see a normal fundus photo, and on the right, you see that the model mainly looked at the fovea followed by the posterior pole and the mid-peripheral area to make a diagnosis, similar to what us retina specialists and ophthalmologists look at when making a diagnosis. The case of a hemiretinal vein occlusion showed consistent findings. The model focused on the superior areas of hemorrhage and also looked at the vascular arcades, which are often affected in retinal vein occlusions. Retinitis pigmentosa was interesting. The model looked at the mid-peripheral area of the pathognomonic diffuse bone spicule-like pigmentation. It did not assign much importance to the macula, which we know is affected only late in the disease process. Retinal detachment showed, again, clinically relevant findings. The model focused at the interface between the attached and the detached retina, similar to what us clinicians would look at when examining a detached retina. To know if our models performed well, to know if ophthalmologist-made models could be compared to those designed by AI experts, we systematically searched the literature to find bespoke deep learning models created by experts. Discussing and comparing our findings extensively is outside the scope of my presentation, but we did that exercise and we concluded that our retinal vein occlusion model that was trained on the Tsukazaki public project dataset did as well as a similar model trained on the same dataset. The case of retinitis pigmentosa, again comparing to an expert designed model using the same dataset, did similarly as well. And although our AutoML model for RD did well, it did not perform as well as the one designed by an AI expert. Nonetheless, we conclude that ophthalmologists without coding experience can design high-quality AI models. Our study is the first to show that models built by ophthalmologists can be equivalent to ones built by experts when looking at ultra-widefield photos. We also show that AutoML tools can detect hemorrhage RPE changes and retinal elevation confidently. And in the future, we'll be looking at the validity of such models, perhaps in clinical practice, and we'll also look into cross-platform generalizability to machines that use true color as opposed to pseudocolor. Thank you.